Hi everyone, this is the quantitative question for mechanics that I will be explaining today. So first I'll start by just reading and introducing the question, and we'll go over some important pieces we want to write down. So to begin,
Obi-Wan uses the Force
to push a 65 kilogram battle droid that is initially at rest off of a spaceship hangar deck. A total force of 5.0 times 10 to the second newtons is applied for 2 seconds before the battle droid is sent horizontally off of the deck. If the spaceship hangar deck is 5.0 times 10 to the first meters above the ground, how far does the droid land from the hovering spaceship? So before we jump into using the problem-solving guideline, we want to look at a few things that are important to us. So some things will seem obvious, like in a basic mathematics question, where we look at things like time is 2 seconds, and then we'll look at some of the hidden information. So first, we can go ahead and look for any values that seem very obvious. So we saw here that a total force of 5.0 times 10 to the second newtons is applied. So we'll want to go ahead and put a box around that value. We also have the duration that it's applied, which is 2 seconds. And make sure that you keep your units in because those become really important. And then another value is the height, which they tell us is 5.0 times 10 to the first meters. Okay, next we want to look at things that are more hidden, so not as obvious as these values. So we have things like it is sent horizontally, so that tells us our direction. And we have that it's initially at rest, which tells us its initial velocity. And we know that the deck is above the ground. And then we, of course, have our question at the end, which asks us, how far does the droid land from the hovering spaceship? So from that, we know that we are trying to find the change in x. That will be our unknown from all of these variables. Okay, so now that we have read the question and reviewed our known values, we now want to list those, and we also want to list what we don't know about the problem. That way we can get a sense of direction moving forward to what the main concept of the problem is. So to begin, what we know is that the initial value, the initial velocity in the y direction is 0 meters per second. And the velocity initially in the x direction is also 0 meters per second. Following that, we also know that the mass of the battle droid is 65 kilograms. So let's go ahead and write that. Mass From that, we also know that the total force is 5.0 times 10 to the second newtons. So and we also know the period, which is 2 seconds. So we can write period equals 2 seconds. And notice that I have still kept my units all attached because it's very important when we go to solving this problem. For the unknowns, we do not know the change in x, right? Because that's what the question's asking us to find. We also don't know the change in y, which is the change in the height. We also do not know the acceleration in the x direction. And we do not know the acceleration in the y direction. Following that, we do not know the time. That looks like enough. We do not know the time, and we do not know the final velocity. Also, we do not know, the final velocity. So from these lists of known and unknowns, we're going to move on to what our main concepts will be. Also note that there is one unknown here that we do know, but that comes with a concept about acceleration. So some of you might have noticed that the acceleration in the x direction is actually 0 when we talk about projectile motion, which this problem is dealing with. So that will be a note just to keep in your mind as we move forward. Okay, moving forward, we're going to talk about the main concepts that this problem is dealing with, which you will notice is part A on the problem solving guideline. So when I think about the main concepts, I like to look at the equation sheet, which I have right here, and I'll be sure to post a copy of this on the website, but you will have it available to you as well on Canvas. So first I look at our knowns and unknowns, which we just talked about, and I try to look at what equations deal with those variables. So something that I first notice is that it deals with 2D kinematics, because on the equation sheet, we can see equations that deal with velocity in the x, time, acceleration, velocity in the y, final velocity, all things that we're going to need to understand in order to get into our change in x. So because of that, I know that one of the main concepts that this is dealing with is 2D kinematics. So I'm going to go ahead and take note of that. And this problem is a great example of how some of the knowledge is going to build on each other because, as you probably know by now if you're watching this video, 2D kinematics is taught very early in the quarter, and at this point you've moved quite far beyond that as you're learning gravitation and things like that. Okay, second to that, we want to look at other unknowns. So the problem gave us total force. So from that, I understand that there's going to be some force equation that we're going to need to understand and find. So I go ahead and look at my equation sheet again, and I see that we're going to be focusing on force. What's important is that forces, that's a very broad subject, so we want to narrow that down so we can stay more focused. Since I know that the total force is F equals ma, I can relate that to Newton's second law. Alright, and then that will be it. Alright, so now as we begin to jump into the problem solving guideline, we need to understand the assumptions we have to make to solve this problem, because in physics we have to do a lot of assuming in order to solve. Okay, so first we understand that we're going to be using our kinematics equations, which means that in order to use those, we have to assume that acceleration is constant, because if you look deeply at all of the equations, they only work if the acceleration is constant. And since we're dealing with projectile motion, we know that our acceleration is little g. So one of our assumptions is assume acceleration is constant. Next to that, we have to assume that little g is equal to 9.8 meters per second squared, which is the acceleration due to gravity. We're also using Newton's laws. So in order to use Newton's laws, there's a hidden assumption that isn't as obvious, and that is that we have to assume that we are an inertial reference frame, because they cannot be used outside of that. Alright, so before we begin solving for anything, we need to understand what the question is asking us. So this question particularly is asking us how far the droid lands from the hovering spaceship. So before we talk about this quantity, I mean, it seems very straightforward, but I drew a very simple picture. It's not necessarily completely the picture of this problem, but assume we have some object A that is somehow pushed off of some height h. It will have some projectile motion this way, and it will land somewhere here at time final after the initial time. Because of that, we have some distance, delta x, right here, where our object has actually moved away from its starting point. So because of that, we can now relate that to our problem, where it's saying we have this battle droid of this height, and we push it off with this amount of force. How far does it land? That's asking for this value here, delta x. So the quantity we're solving for is our change in x, which is our change in horizontal distance, which is in meters. In physics, we like to keep everything in the metric system. In the US, that's not particularly maybe something you're comfortable with, but instead of having feet here, we're gonna have meters. So we will have the change in x in meters. And please keep in mind that our units are very important. That's why I underlined it. The more that you get used to using your units, the more cohesive your problem solving will be. All right, so in physics, we like to predict our possible answers. Because of that, it will give us a more cohesive understanding of our problem, and at the end, if we have a solution that seems very wacky, we can go back and backtrack. Okay, so my prediction will be based off of what we know. So we know that the battle droid is 50 meters above the ground, and that it travels some horizontal distance x. Because of this height, I'm going to better understand this delta x. So I'm going to say that delta x is greater than or equal to 60 meters, but less than or equal to 30 meters. What this means is that my delta x can lie wherever within this. So if I get to my solution and I say that is nowhere near, say I get 400 meters, I'm going to say I think I did something incorrectly. So this is a very important step of the problem solving guideline. In physics, it's really important to draw a picture so that we have a better understanding of what's going on in our problem. Sometimes I even choose to draw the picture before everything else, whether that be on an exam or a web assignment or even preparing for the exam doing these quantitative problems. So to begin, let's go ahead and draw the tower that the battle droid is sitting on. So I'm going to go ahead and draw this tower, and right here we'll have the battle droid, and I will name it M. Because earlier we defined that we knew the value n of the battle droid, so I want to keep my variables consistent. From that, we also have a height of h, and we also know that there will be some distance x. So I'm going to go ahead and draw that here. And in our pictures, right now this doesn't look like anything's happening, so I want to show the motion that is happening. So I'm going to go ahead and draw these dashes that say there's some projectile motion happening. In addition, we want to take note that there is some force happening on this mass n. So I'm going to pretend it's a hand. Even though that's unrealistic, it'll help me remember. So I'm going to draw a hand here, not an artist, and it's going to be pushing in that way. So from this, we have a pretty good idea of what's happening to our battle droid. In addition, we need to define our coordinate system. So whenever we draw a picture, we want to know what direction is what. So I'm going to write our coordinate system here, where we will have our typical x and y graph that you guys are probably all very familiar with. As we begin to consider how we're going to go about solving this problem, we need to understand what equations to use. So here I have the equation sheet, which I told I would make available on the website, as well it will be available to Canvas on you through the course. So first I have written out all the unknowns, which we talked about previously. And one note I want to make is that I previously said that we did not know delta y, which was a mistake on my part. We do know delta y, it's told to us in the problem. So moving on, I'm going to look at these unknowns and look at the equations we have to think about what we mean. So I see here that we do not know our acceleration, but we do know our force and the mass. So I'm going to say one of the equations we need is, which is Newton's first law. Next to that, I know that we're going to need the velocity, so we're going to have, and from this you can recognize that we do not have the time. So in order to find the time, we will need to use and we will also need to use that the final these are all kinematics equations that you can find on your equation sheet, and we will also need and this is all in the x direction, this is all in the y direction, okay? And from this, we also need to remember our units. So I will write those in very quickly so that we make sure not to drop those. So this is it.
Alright, so as we begin to solve our problem, we first want to find our solution in variable form. So I have written out two equations that I have already rearranged to make this easier, and I have also, for my own convenience, written out these certain variables so that I don't have to waste time typing them. Okay, so first, to begin this variable form process, we're going to write out our equation of vy squared, which equals 2ay times delta y. Alright, so this equation is essentially what we will be working with in order to break it down all the way to delta x equals one thing, because essentially we want an equation that says our unknown equals this, and we want it to be something that we can plug in values we already know. Alright, so next to that, we will have just the final velocity y, which will be equal to now, since we're taking the square root, it will now be equal to the square root of everything in the previous equation. Alright, so from this we're going to put in some known values. So we're going to have our final velocity in the y direction, which will equal 0, because our initial y velocity is 0 as described in the problem, and this will be plus the acceleration in the y direction times time. Alright, moving forward, we will now have that the square root of 2ay delta y 2a delta y will be equal to the acceleration in the y direction times time. And at any point, if you feel that you need to take time and slow this down for yourself, please feel free to pause. Alright, so moving forward, we will now have the square root of 2ay, or 2 delta y, my apologies, it's a triangle, not an a. So 2ay times the square root of acceleration in the y direction divided by the acceleration in the y direction. Okay, so now that we have made quite a bit of progress here, we're moving closer to our solution. This here will all be equal to the time, and then we will get that the square root, here we're trying to find the value t so that we can use it to find delta x. So here we will get that t is in fact equal to the square root of 2 delta y all over, or divided by, the square root of ay. Alright, this is very helpful in our final thing here. So now we will have that delta x will be equal to the total force in the x direction divided by m times the time, which we declared earlier is in fact the period, so I'm going to note that again, which will then again be multiplied by the square root of 2 delta y divided by the acceleration in the y direction. And that's all under the square root. Alright, so here we have our final equation, and
Alright, so as we begin to conclude our solution, I want to go through the problem solving guideline and make sure that we've hit all the points. So first, we talked about the given and hidden information. I wrote out the problem and we boxed in the information that we knew. Then we went over the main concepts. After that, we considered our assumptions because we discussed how physics is based on a lot of assumptions. Then we defined the quantity that we're solving for because in order to solve, we need to know what it is we're looking for, which will also help us as we move along the guideline. We also need to make a prediction so that we understand what our answer should look like. And we need to draw pictures so that we can visualize what's happening, which we did. And we need to find the equations to solve. So we looked at our given and hidden information and what we didn't know, and we came together with a list of things that would help us solve. And then we worked in variable form so that we could have a more cohesive understanding and a much more easier plug and chug version of the problem. And lastly, we will find a solution by plugging in the numbers and solving.
okay, so now that we have found our final equation, we're now going to plug in our values, and we will get that delta x is equal to 5.0 times 10 to the second, which ends up being just 500, divided by 65 kilograms. So we times the period, which is 2, and then times the square root of 2 delta y, so we'll have 2 times 50 divided by the acceleration in the y direction, which is 9.81 meters per second squared. And from this, we're going to find out that delta x is indeed roughly 49 meters. So what that tells us about our problem is that the battle droid fell 49 meters, or landed 49 meters away from the table.